Hello, I will be presenting my seminar on the first in-human study of safety and viability of intraocular robotic surgery. So robotic surgery inside the eye. It's a paper written by Edwards et al., who works at Oxford University, and the paper was published in Nature Biomedical Engineering. And I will be presenting this as part of my undergraduate biology seminar, supervised by Dr. So first, I will give you some background on manual retinal surgery. I will describe the two procedures that are studied in this paper. Then we will talk about the available robots used in surgery in general. Then I will mention a bit of materials and methods, how the study was performed. I will show you the results of the study, which involve the time the robotic surgeries took and their safety. And finally, we'll discuss these results and the impact of the study on gene therapy, which is also mentioned in the paper. So first about retinal surgery. The eye is a very delicate organ with the retina, which is of course a neural tissue. The macula, which is in the center of the retina, where the cones are the most concentrated, has a thickness of less than 252 micrometers, and the thin inner limiting membrane, which is the top membrane of the retina, is only 20 micrometers, and this is important because a human tremor, so how much the surgeon moves his hands involuntarily, could go to 100 micrometers. Hence, big tremor could pierce around half the retina and could damage vision a lot, since all the cones are present in the macula. Now, this picture is called an optical coherent tomography, and we'll see a lot of them during this presentation. So the first procedure studied in this paper is the removal or peel of the epiretinal membrane. Now what happens is, with age, the vitreous becomes more liquid, it loses viscosity, and as the person moves, the vitreous moves inside the eye and it damages the retina. So then the retina produces scar tissue, which forms above the macula. I don't know if you can see it because of the light, but if it's here, if you're close enough, you can see the scar. And it's, of course, it blurs the vision of the patient. The procedure is to do a vitrectomy. So it's an operation on the vitreous. The surgeon inserts the needle inside the eye and peels the whole membrane. The second operation is the inner limiting membrane peel. The inner limiting membrane is natural. We all have it. It's the top layer of the retina. But what happens here is, with age also, the vitreous shrinks, but it's still stuck to the retina, so it peels it away and it tears the macula apart and creates a hole in the macula. And it is thought that removing the inner limiting membrane, which kind of obstructs the closure of the hole, will promote its closing. However, during my research, I've seen that recently they're discovering that removing the inner limiting membrane does not actually help. It's not necessary anymore to do it, but surgeons are still used to it and they like doing their job. Now some background about the available robots in the field of surgery. As you know, the eye is a small organ. Its volume is only 6 centimeters cubed, and it's characterized by high rotational mobility. So it moves a lot inside its socket, so it's hard to stabilize. Now, the most famous robot used in the world is the Da Vinci, which is pictured here. The UBMC has one of them, and they use it for big operations in the urology and the OB/GYN departments. So it's a big robot and we cannot use it on the eye. So the authors considered 4 types of robots for the study, and the first type are the handheld devices, which improve steadiness thanks to the gyroscopes here. Now, a gyroscope is a device that maintains orientation and angular velocity. As the surgeon moves his hand, the device does not move. Maybe you've seen spoons for Parkinson patients, or more generally in cameras, and when they film movies, they have these kinds of gyroscopes to stabilize it. The problem with this handheld device is that it's not precise enough. The second type are co-manipulation robots. And here, the tools are held, like the needles are held by the surgeon and the robot simultaneously. So the surgeon will move his tools, and the robot will hold them a bit. So these robots help in tremor filtering, reduce the tremor, as we saw before, it was 100 micrometers. However, these robots do not have safety boundaries because they are mostly mechanical. They don't scan the eye, they just hold the tools. That's all they do. The third type are telemanipulation. We also call these master-slave systems. The master, of course, is the surgeon who controls the slave, which is the robot, from afar. So here, this system is completely digital, and the robot pictured here could be an answer to the Da Vinci because it's much smaller.
Where's the robot? Is the one with the eye, the beige thing?
The robot is,
okay,
this is one arm.
This is okay.
This is the camera.
Yeah. Oh, that's what I saw.
The fourth type are magnetic microrobots. You would think that this is the future. They're precise. They work with these 8 magnetic coils, and this is what the robot looks like. You inject it in the eye and it works alone. The problem with this kind of robot is that they cannot carry large objects. Now, as I described the 2 procedures before, what do you think a large object could be in our case? The more generally, the membranes we want to remove, the anti-retinal membrane, the inner limiting membrane. This robot cannot carry them. It can cut but not carry. It can cut but cannot carry.
Membranes are
Can't be
tiny.
it.
Membranes should be tiny. Right? The eye
The robot is tinier.
The robot is tinier. Eh? This is the robot? This is the
Yeah,
dot?
this is
yeah?
it. Yes.
Yeah, that's why. Yeah, that's why.
So the robot can't feel the
This is a
membrane.
zoom of the zoom.
Can't carry it, no. This can't, no.
It's controlled by the coils.
Yes.
Oh, okay.
So in this study, they used this particular robot. It's called Precise. It took me 3 days to notice the pronunciation of the word. It was designed by some of the contributing authors in the Netherlands. It was tested on animals like pigs, and it had promising results. Now this robot is a master slave. Now you think he's controlling something, but no, that's just a light. It's called an endo-illuminator, and it's just a fiber optic light. Now this is the robot that does the operation, and he controls it with this remote here. So he doesn't touch the robot, it's not co-manipulation. This robot, of course, has tremor filtering.
Do robots tremor? I don't think
No,
so.
robots not at all.
Really,
But
not
it's
at all.
the hand. If he moves his hands like
it will
this,
filter.
it
It
will
will
filter
filter the hand.
the hand. It has dynamic motion scaling. Now this is the most important. This is what led us to create surgical robots. The surgeon can move his hand with big movements, and the robot will only move a little bit. So it even has different speeds. As it enters the eye, it's fast, but then as it gets closer to the retina, it moves in smaller increments. The robot has virtual boundaries because it's smarter than other robots. It can scan the eye, and it creates its own boundaries so that the surgeon doesn't pierce deeper than he should. And finally, it has something called a clutch mechanism, and this allows the needle to freeze in space, in this 3D space, and memorize where exactly, what coordinates, and in which patient it can remember these and put them in its database. Now, this is a closer view of the robot itself. As you can see, it can move in all directions and angles. My hypothesis is using robotic assistance improves microsurgery of the retina in a safe and viable manner. Now let's talk about a bit about materials and methods. To do this study, they enrolled 12 patients. 6 of them needed an retinal membrane peel, and 6 needed an ILM peel. The patients were randomly assigned to either robotic or control. And the 2 procedures were chosen not because they absolutely need robots, but because they are well-known routine procedures with high precision steps, and the surgeons can easily integrate robots in these steps. This is the operation room setup. It might not look important for us, but for the surgeons, the robots didn't affect the setup too much, thanks to its small size. As you can see, this is the only space taken by the robot, much smaller than the patient in comparison to the Da Vinci, which is really huge.
Is it local anesthesia?
They actually had to give general anesthesia because they were scared that the patient might move his whole head. But then we discussed that he could have done local anesthesia. It's just for precautions. They also taped the heads of the patients. This is a picture of the robotic setup. You can see here the instrument manipulator. So this is what holds the tools. This is the motion controller, the remote control here. And here you can see the surgeon holding the endo-illuminator, and we'll talk about this later when I show you the video. Now the docking, stabilizing of the tools. This cannula was inserted by hand, and then the robot was docked into it. This white object belongs to the robot, and it helped stabilize the needle inside the eye so that if the needle moves, it doesn't pierce a bigger hole than the cannula. And so in that way we don't damage to the eye globally. And here we can see an OCT of the ERM peel. You can see that the
What's an OCT?
Optical coherent tomography. I was going to ask you to see if the others. So here we see that the retina is a bit peeled. So I'll come back to these results one by one. So first I want you to observe the difference in movement. Here we're looking at the tremor between robotic on the left and manual on the right. And another difference is that on the top video we're using an endo illuminator, which is handheld, as I showed you before, while on the bottom we're using a chandelier, so it's a stable light source. And as you will see again now,
More tremor on the right, for sure.
yes, and even between the endo illuminator, no, it's frozen, but we'll come back. Even using the chandelier reduces a lot of tremor caused by the endo illuminator. Now, all robotic operations were successful.
How is success measured?
Success is measured as if the hole closed or not after a month for the INM, and the epiretinal membrane if vision came back to normal. So here, 1, 2, 3, and 6 are INMs, while 4 and 5 are ERMs. You can clearly see in this one how the macular hole is big, and now it's closed. This is the normal shape of the macula. Here you can see the inner limiting membrane above it obstructing the hole. And here it's clear also the retinal membrane, how it's blurring everything.
So which one is with the handheld, manual?
No, these are all the robots.
Oh, all robots.
Sorry, maybe you can't read. This is baseline before the operation.
Before and after.
And this is 1 month after.
Okay.
Why do you think we have more INMs than ERMs here for the robots? Why do we have more INMs? We have 4 cases of INMs and only 2 cases of ERMs for the robots.
But they were 6 when we started. Oh no, 6. Robots.
Yeah.
Okay.
It's because they were randomly assigned. So this, by luck, we didn't get 3. Now the most interesting results. The time difference was significant between manual and robotic surgeries. So from the point of entry, when the needle entered the eye until it reached the retina, it took 12 seconds for the control and 2 minutes and a half for the robots. Then removing the membrane took 1 minute 20 for the control and 5 minutes for the robots. And the total operation mean time was 31 minutes for the control and 55 for the robots. So it took double the time to do the same operations. They also counted the number of microtraumas and microhemorrhages. Microtrauma is when the needle accidentally touches the retina and causes some bleaching. Microhemorrhage is when it causes some bleeding. So these are accidents caused by the surgeon. The median number was 1 accident for the control and 0 for the robots. However, they have exactly the same range, 0 to 2. So the number of accidents was insignificant. There was no significant statistical difference between robots and manual. Hence, a surgeon could have half the number of patients for minimal improvements in safety.
How can microtraumas in robots be 0 and yet the range is 1 to 2?
No,
How is this special?
there are 6 patients.
Tiny.
So 4 of them had 0 accidents.
4. 4 of them. Okay,
Yeah.
okay. Okay, so there is patient variation. Okay.
Yes.
Okay.
4 patients had 0.
I thought these were means.
No,
I thought
no, these
the
are-
0 is a mean. Okay.
And the green line is the median.
Mhm.
So it's 0 and 1.
Mhm.
A summary of the results. The virtual boundary allowed higher z-axis precision. The z-axis is the up-down axis. So the surgeon doesn't go too deep down. The eye was more stable, especially thanks to the chandelier. Both robotic and manual surgeries were successful. The duration was significantly different in favor of the manual surgeries. The accidents were insignificantly different. Well, you could say they were not different. And the surgeons enjoyed the clutch mechanism and other smart features of the robot. Now let's discuss these results. Precision and accuracy were definitely improved with the robots. And this was noticed, this was observed thanks to the motion scaling, the decreased increments as the needle approached the retina. And why didn't we find a lot of difference in the accidents, the microtraumas? It's because these procedures are well-known surgical procedures. The surgeons have decades of experience doing them, and it's their job not to have accidents. Why was the time so different? It's because the surgeons had some bias against the robots because they were scared of using them for the first time, and they preferred to go safely and slowly instead of fast. Although the robot was definitely safe, it has virtual boundaries, it could have gone faster. Now, the biggest issue when we talk about viability, because this is half of what the paper wants to search, is money. And insurance companies will not accept paying more for operations that can be easily done by hand and with no extra cost and with no accidents also. Some limitations of this study include the small sample size, we only had 12 patients, and the lack of previous experience with robots. The surgeons were trained with animals right before the study. Now, what these results mean for the future is we should find another way to use the robot, maybe gene therapy, using some features I talk about. I talk about them. It's the robot can say, as I said before, that the robot can save its position in the 3D space of the eye. So it can come back to exactly the same hole it pierced in the retina after a month if the patient has many sessions in the gene therapy. So what they did in this study is they used the same robot to inject a tissue plasminogen activator to treat submacular hemorrhage. Now, this is age-related. The macula degenerates with age, and it results in hemorrhage, which is of course bleeding or blood clots even under the retina, under the bottom layer, which is the retinal pigment epithelium, and the choroid. They injected a medication called alteplase, which is this tissue plasminogen activator. It activates plasminogen, becomes plasmin, and plasmin, as you might remember from biochemistry, degrades fibrin, and fibrin is found in the blood clots. So plasmin will degrade fibrin and remove the hemorrhages. This is a video of the procedure. The nice feature they used is the positioning. So the clutch mechanism. They could put the needle somewhere, park it. The needle will stay in its exact same position, and the surgeon can safely and slowly turn to the medicine. We'll see it over here at some point. Now, as you can see now, the problem with OCTs is that we do not have a 3D vision. The surgeon cannot see in 3D. He can see in vertical and horizontal, and he must guess a bit how to perceive depth. So here is the needle. It has been inserted in the retina, and as you can see, it's completely stable. And this time, you can inject the medicine. And here you can see an air bubble. After the operation, they tell the patient to sit in a certain angle so that the bubble goes on the hemorrhage to release some pressure. So the robot's increased precision allows for the injection of the medication with no significant time difference. As you can see, the robots took 8 minutes and 3 minutes, while the hand operations took 4 to 6 minutes. This is not a significant time difference, unlike the ERM and ILM. So in this gene therapy, there is no time difference, and we can do as many operations as we want in a day. If you're wondering what logMAR means, it's a logarithm of minimum angle of resolution, and that's just the chart we see at the optician with the letters. A score of 0 would mean that you have perfect vision. So as you can see, the score decreased every time. So to make these, to include robots in the surgery field and make them cost effective, they should be used in an assistive manner, only for high precision steps, and they should be able to be parked away and brought back when needed during the operation. They should fit inside existing operation rooms, because if a hospital had to open a completely new room just to put a robot in it, they would waste millions of dollars. So, and the robot should fit in an existing room. One robot should also be able to do various procedures, because $1 million robot which only does one operation is useless for a hospital. It should also be able to do automated tasks. As I showed you in the video before, the surgeon has depth perception problems, while the robot can scan the eye perfectly, and so the robot should be able to use this depth perception to do some tasks alone and accelerate any operations it does. So here are the references I used. This is the paper and these are backgrounds. Do you have any questions?
Lights on, please. Perfect, perfect. Anyone did not understand anything?
No.
No, we understood it. Amazing. You act like you're an eye doctor. Honestly, as if you know. Is it something that you like to do in the future? Is eye operations and things that work? And we've really dug into. Are the videos part of the paper or additional?
Yeah, they were supplementary videos. They are not. I had to click some links to find them.
Okay.
But,
so tell me about yourself. Is this something that you like to do in the future?
I thought about eye surgery, but what I really like is robotic surgery. So this is the only paper I found about robotic surgery. But it happened that I considered ophthalmology for a long time. So this, but I still had to research a lot about the operations. I had to read the papers to see how the operations
You
work.
come across as if you're an eye physician. Really, I mean, you fooled us as if you know it all, which is great. This is the way to do a seminar. So I'm opening the floor for questions. Go ahead, please.
I didn't understand when we were talking about the microtraumas, and we were comparing between the physician operations and the robot-assisted operations. We noticed that the median for the physician operations was 1 microtrauma per operation and 0 for the robot. So how did you conclude that it doesn't make a difference?
Because when you analyze them with statistically with the chi-square test and everything, this is not a significant difference.
Okay. One more question. Because, you talked about gene therapy.
Yes.
So what it helps in gene therapy is just that it administers the drug in the same location. That's the purpose.
No, the medication activates the plasminogen gene. So
yes, I understood that the purpose of the robot in this is
to put
it in the same location.
Yes.
Because it's able to memorize the same location.
Yes. So when a patient comes and he has a lot of sessions, every time he comes in the operation room, the robot can go to exactly the same location, inject it, and go back. Sorry. Yes. Yes. By itself, it can remember the pathway it took. Yes.
This I didn't really understand what the microrobot can do. If it can't heal, could it deliver gene therapy? Perhaps it could deliver something.
No, it can only cut.
It could cut.
Yeah. So this is this maybe in 50 years it can do more, but until now it doesn't do much.
So what we conclude from the study is that the robots are very useful for dangerous operations, but they're not useful for regular operations.
Yes, exactly. In these well-known operations, we do not need robots.
I was going to answer that question. The success rate, how did you measure the success? The paper, how did you measure it?
We have 2 factors, safety and viability. Now, safety, it is safe, but it is not significantly safer.
Yeah, exactly. You said in the paper states that the differences between the mortgages, the damages, it's not that safer. And when we're talking about time, the doctor... It takes more time for the robot, so we can just do it by hand.
Only because it's a new technology. I think with time it's going to be
there's a lot
less
of
time
bias.
consuming. Yeah.
But so how does the paper defend that? How does the paper claim that the robotic surgery is better than the manual? If a physician can do it more faster?
I understand the question. It's not, the paper doesn't say that this is best. The paper wanted to see if it was best, but it turned out that it wasn't. For the 2 well-known procedures that are IPRM and ILM. However,
so the hypothesis is rejected?
Yes.
Ah.
It is safe, not safer, but it is not viable. For the well-known procedures.
And by viable you mean?
money, time.
So that's why the insurance companies do not support it.
Yes.
Yeah. So, sorry. Follow up from this paper. Anyone has bought such a robotic system for the hospital? Did you follow up just to see if any hospitals have clinically implemented them in their hospital?
The robot is actually still a prototype. So the only way they could use it in this study is by having the contributing authors.
They make it themselves. Maybe they're engineers.
Yes, actually.
Engineers. Yeah, biomedical nature, biomedical.
So I can name them actually. Meaning, Bielen Naus and this guy, Simonovich. These are all the engineers from the precise company.
They made it.
They made the robot that they use it.
So
yes, no, just for what they were talking before, this means that gene therapy is considered as a dangerous.
Yes, gene therapy could be dangerous because we have this time, unlike the two others, in this one you have to actually go under the retina. So you have to pierce it all. And you're using a much smaller needle for this. And to minimize damage to the retina, it would be really perfect to go in the same hole every time we come back.
So the robot is doing it better than the human in this case.
Yes,
for sure.
yes.
For gene
therapy, it's better.
Just the question concerning the time. Yes, it's usually that the more time the procedure takes, the less safe it becomes, or because there's
No,
high
more
risk.
time it takes, it's safer.
Safer.
But it's not significantly safer because, as we saw, the manual surgeries do not have accidents. So it doesn't. So
but for
it's already safe enough.
Yeah,
It's
but for
already
a
safe.
starting physician, I think for a starting physician, it's safer to use a robot.
Yes, definitely.
These are very well, trained and experts in their field, and they've done so many hundreds or maybe thousands of operations,
And
so they know what they're doing.
It makes their job a little
But
bit
they
more
didn't
fun.
test starting physicians. I think if
No,
they had
they're-
tested starting physicians, maybe the robotic
No,
system would be better.
They're well-known ophthalmologists at Oxford, so
This is the only study that's been done on the robot.
on retinal, retinal surgeries, yes. But you have a lot more studies on other things. The Da Vinci is 19 years old now. It was created in the year 2000, so it's very developed for urology and gynecology, but not for the eye.